Hello everyone, this is Frank Jenkins. In this video I will be discussing modeling with differential equations. The problem that I will use throughout this video is taken from homework 1 in our web work assignments, problem number 2, and the question reads, dead leaves accumulate on the ground in a forest at a rate of 4 grams per square centimeter per year. At the same time, those leaves decompose at a continuous rate of 70% per year. And the question asks us to write a differential equation and sketch the behavior around the equilibrium point. Okay, first of all, I will write the differential equation. The question tells us to use Q to represent the quantity of leaves, dead leaves on the ground at any given time, which is represented by T. Differential equation is of course a derivative, which represents the rate of change. In this case, to model this, we simply want to know the accumulation rate minus the decomposition rate. Okay, so our accumulation rate, as given by the problem, is simply 4 grams per centimeter squared per year minus 70% of our quantity, again represented by Q. Now, before I solve this, I just want to show the behavior around the equilibrium point. First off, I did a direction field using the applet. The numbers are too small to see on the video, but you can see the equilibrium point, which is 5.71, and you could see that it's a stable equilibrium. This is better demonstrated by the phase diagram I did. Now, to do this, we would simply set the differential equation to 0, okay? And when we solve for Q, we get 5.71, and that would be our equilibrium. There are also other techniques. If it's a more complex equation, we may factor, and we may find multiple critical points and so forth. But in this case, we just have one equilibrium point, which is 5.71, and we see when we test values above 5.71, we see it's decreasing. For values below 5.71, it's increasing. So we see that this is indeed a stable equilibrium. Okay, now to solve this, there's a variety of techniques I could use. For instance, I could use an integrating factor. I would just move my negative 0.7 Q to the left side. My P of X would be 0.7. Integrating factor would be E raised to the integral of 0.7 dt, and so on. But in this case, I'm going to just use separation of variables. So we would begin by multiplying over our dt and then dividing our expression over to the left side, which will look like this. Okay. FYI, I wrote a lot of this out due to the time constraints. Okay. Now, we don't necessarily need to put the 1 here, but there is indeed a 1 here because when we divide this out, we get a 1. And this would actually be the solution. Okay, I wrote the E in red just to point out that it's actually not part of the solution. I do want to point out one sort of minor complicating factor with this that has to do with this expression here. Because of this negative 0.7 in front of the Q, we're not in the form we'd want to be in, which is du over u. So in order to do that, we would typically have a negative 1 over 0.7 outside of our integral, and then we can have a negative 0.7 in our numerator. But in this case, for the sake of brevity, I just included this in the equation. Now, to get rid of this natural log, we would simply use our exponential function, which will yield, okay, we're going to raise this expression to this term here. And that's how we handle this in the context of a natural log. Okay. Now, because I got rid of the absolute values here, we're going to make this plus or minus e to the t plus C2. Okay, and I make this C2 because we typically have to continually change our values of C. So here I'm going to say C1 equals plus or minus e to the c2. Okay, and this will just simplify the expression, as you'll see in just a moment. Now, to get rid of this very ugly expression here, which would make this problem very difficult to work with, I'm going to simply raise everything to negative 0.7. Okay, and that just makes this 1, which is very nice, which yields the following. And we see this expression show up here. Okay, and that would actually be our implicit solution. In order to get our explicit solution, we just need to do some minor algebraic manipulation. All right, so we would subtract the 4 over, and then we would divide out the negative 0.7 to move it over to the right side. Okay, and that is sort of simple algebra, so I'm not going to do that here. But it would yield a general solution of okay. And now, in order to get our particular solution, we would have to solve for, actually that would be C1. We'd want to solve for C, okay? And we do that by simply setting our time to 0 and setting the entire equation to 0. And when we set t to 0, this entire expression becomes 0. E raised to the 0 is simply 1, so that just goes away. We just have c multiplied by 1. And when we set this expression to 0, we will see that c equals 5.71. And that gives us what we need for our particular solution, okay, which is, well, we can actually factor out 5.71. Okay, and that is our particular solution. Hope you enjoyed the video.